We are Team HAL9000 presenting for AIAA's project for an orbital exploration at Pluto Shadow System. Our spacecraft for the mission is Lowell's orbiter, named after Percival Lawrence Lowell, who detected but could not discover Pluto by the end of his life. Because of the inclination of Pluto's orbit around the Sun, Pluto is progressing further away from the solar system ecliptic plane. As it takes about 161 years to come back to the plane, it would be preferred to visit this planet before it's too late. The spacecraft's main objective is to insert spacecraft into an orbit around the Pluto-Charon system as requested by the RFP. Also, the spacecraft has 5 more mission objectives that are not specifically requested by RFP. They're selected with consideration of new findings at Pluto-Charon, categorized into primary and secondary by the priority of the objectives.
The mission has 7 main requirements. The orbit within the Pluto-Charon system will have a periapsis altitude of 100 kilometers, allowing for close data collection. Instruments will record hemispheric panchromatic mapping of the entire surface of Pluto with resolution exceeding 1 kilometer per line pair, and surface color images with resolution of about 3 kilometers per line pair. The spacecraft systems will be capable of a total delta V of at least 6.18 kilometers per second. Instruments must be kept at a 10 to 30 degrees Celsius. All instruments must be radiation hardened, and all communication systems will use X-band frequency and will have built-in redundancy. There are 4 main constraints on the mission, which are listed in the request for proposal. The mission must not last more than 25 years, propulsion systems must have a TRL of 6 or higher, the mission must only use a single launch vehicle, and any instrument substitutions must be scientifically justified.
The spacecraft will leave the Earth on February 2030, and it will not involve parking orbit but go straight to cruise space so that the launch vehicle also covers the delta V to escape the Earth. This also allows the spacecraft to carry less fuel tank, which makes the spacecraft design more reasonable. Then it will fly by at Jupiter on July 2031, taking a year and a half. The spacecraft will aim at the latitude of 16.6 degrees from solar system ecliptic plane so that the plane change can occur heading to the arrival at Pluto. It will reach Pluto on December 2051 with at periapsis altitude of 100 kilometer, eccentricity of 0.75, which is highly elliptical, with execution of delta V of 4.78 kilometers per second. Then, with mission length constraint of 25 years, the spacecraft will continue data acquisition and transmission for 3 years and 2 months at Pluto system.
The structure subsystem is responsible for spacecraft design and assembly, as well as protection from space environment for the fuel, power, and other components on board the spacecraft. The satellite structure is a 300 kilogram aluminum and titanium cylindrical structure. Its dimensions are 2 meters in diameter and about 4.5 meters in length when launched. The main satellite body features a 1 millimeter thick aluminum shell with a titanium fuel tank inside. The structure contributes 188 kilograms to the structural mass. The external fuel tank holds the fuel and thrusters needed for the insertion burn. Similar in structure to the main satellite body, the mass of the external tank weighs in at 111 kilograms empty. This mass is jettisoned once the fuel is exhausted through the insertion orbit burn. The entire system is integrated around the RTG, which heats and powers the spacecraft. The external fuel tank wraps around the RTG and is attached to the main satellite body through the heat sink, which regulates the spacecraft temperature. The satellite's instruments are attached around the outside of the satellite on an aluminum ring. Overall, the structures of the satellite feature a cylindrical main satellite body and an external fuel tank which will be jettisoned. The 300 kilogram structure protects and supports all the critical system components which are needed for the mission.
New Horizons used the Atlas V rocket to send its payload in a flyby trajectory past Pluto. A larger heavy-lift launch vehicle will be required to provide the extra C3 needed to conserve as much onboard propulsive fuel as possible. By comparing launch vehicles using low Earth orbit as a reference for lift capability, the Space Launch System, or SLS, was chosen as our launch vehicle. Our mission will be using SLS Block 1, which is slated to launch in December 2019. This is 11 years before our mission start date, which gives plenty of extra time for any unanticipated setbacks. According to the table displayed, Block 2's initial launch will not take place until approximately 2030, which is far too close to our launch date to be considered viable. The figure displayed demonstrates that for missions requiring a large characteristic energy of approximately 160 kilometers squared per second squared, the Block 1 surpasses the Block 1B, therefore making Block 1 our chosen launch vehicle. The SLS Block 1 consists of 4 RS-25 engines on the core stage with 2 solid rocket boosters attached. each of which add 3.6 million pounds of thrust. For this mission, the interim cryogenic propulsion stage is required as a second stage to supply the extra characteristic energy required for our mission.
The propulsion system must support the satellite throughout the course of the entire mission. It is responsible for the insertion burn, trajectory control, as well as attitude stability and control. With no control wheels on board, the thrusters are essential to the spacecraft. Lowell's orbiter features the MR-80 as well as 16 redundant MR-111 thrusters for control, with 8 for redundancy. Many fuel sources were considered, but hydrazine fits the long mission profile best and is capable of being turned on and back off again, as is necessary for the small control thrusters. Lowell's orbiter uses a nitrogen pressure-fed system to deliver fuel to the thrusters. The two thrusters chosen are the MR-80 and MR-111 by Aerojet Rocketdyne. The thrusters are both flight-proven as of now and are able to use the same fuel source. The MR-80 provides up to 3,100 newtons of thrust for the main insertion burn, and the MR-111 are appropriately sized for attitude and small orbital adjustment.
The mission will be using NASA's Deep Space Network. The Tombaugh Science Operations Center will be used as a payload operation control center, while the Johns Hopkins Applied Physics Lab will serve as the Space and Missions Control Center. NASA's Planetary Data System Archive will be used to store and later analyze the data.
The communication systems include 2 low-gain antennas for near-Earth communication, 1 medium-gain antenna for redundancy, and a high-gain antenna to transmit the collected data. Commands and data transmission will use the X-band operating frequency with the Deep Space Network. It was assumed that all the instruments would function throughout the entire mission and would be collecting data for 16 hours per day. It was estimated that there would be 8 hours of downlinking time per day. The high-gain antenna will have a limit of 82 watts of transmitting power at any time while in orbit. Link budget calculations showed that with this power, Lowell's orbiter can achieve a data rate of 3,500 bits per second with a 2.1 meter diameter high-gain antenna. These results are demonstrated in the graph shown and are compared with the New Horizons mission parameters. Lowell's orbiter could transmit 0.12 terabits of data to Earth before the end of the mission and will not have time to send back about 9.7 terabits, which could be stored in onboard solid-state recorders. At the mission's end, the decision could be made to extend the mission length solely for the purpose of transmitting any of the stored data. These data size estimates are the upper limit, since the actual data amount will be lower due to compression, processing, corruption, and duplicate data. A more efficient way of sending back such large amounts of data would be through laser communication technology, which will be tested on NASA's Psyche mission in 2022. However, these X-band transmission calculations show the worst-case situation, which is a maximum data size and slow data rates.
Command and data handling breaks down in 3 main parts: onboard computer, the memory recorders, and the flight software. The communication subsystem will be highly affected since the transmission rate will depend on the performance of command and data handling. The mission's requirement to map Pluto and Charon with finer resolution than New Horizons increase the amount of data we need to transmit back to ground station. To determine the most suitable computer processor for the mission, a trade study was used. The heritage and memory were weighted heavier compared to other parameters, aiming for reliability. The HAL9000 supplied by Lockheed Martin was selected as the final processor of Lowell's orbiter. It is radiation-hardened and 32-bit processor that was used in many Mars missions, such as Spirit, Opportunity, and Pathfinder. For redundancy, we'll have 2 HAL6000 processors and 2 8GB solid-state recorders. The integrated system will be interconnected using space wire, which, using an advanced semi-autonomous software, will be able to select what data is worth sending back to Earth.
Lowell's orbiter will use the same GMC system that New Horizons used, since RFP calls for the less focus on it. For attitude determination, the spacecraft will use star tracker to calculate the orientation, inertial measurement units to measure the horizontal, vertical, and rotational motion, and digital sun sensors to adjust the spacecraft in case of failure or emergency. 16 thrusters will be used for attitude control. There are 3 different attitude control modes, including straight axis, active spin, and passive spin mode, where the modes will depend on the crew space. For the trajectory determination, porkchop plot was used to analyze the appropriate launch window. Since the trajectory involves flyby at Jupiter, 2 separate porkchop plots were analyzed to determine the trajectory. Through these, the spacecraft shall be able to reach and orbit around Pluto's sharing system as one of the mission requirements.
Lowell's orbiter will be utilizing a radioisotope thermoelectric generator, or RTG, to generate power for the spacecraft. The general purpose heat source, GPHS variant, which was also used successfully to provide power for New Horizons, was selected for the mission. An RTG is ideal for traveling large distances away from the sun where solar power would not be feasible. 12.81 kilograms of plutonium dioxide fuel will produce 4.659 kilowatts of thermal power, which will create a large temperature differential with the surrounding cold environment. This differential will be harnessed by the RTG and converted to electric power using thermocouples. At the beginning of the mission, the RTG will supply 285.4 watts of power. Since the fuel source decays over time, this figure will steadily decrease. Upon arrival to Pluto, 168 watts of electric power is required for the orbital insertion maneuver. The initial power and fuel values were scaled purposefully such that 180 watts of electric power is available for the MR-80 to use. After orbital insertion is complete, the power output will steadily decay to a final value of 168.3 watts by the end of the mission. The RTG provides both electric power for the scientific instruments and heat to warm the spacecraft. A heat shield will separate the RTG from directly facing the scientific instruments to make sure they do not overheat as they function optimally in cooler environments.
Thermal control within the spacecraft adopts its heritage from New Horizons, which requires little to no additional power and is the best form of thermal control for this mission. The onboard electronics must be kept at a temperature between 10 to 30 degrees Celsius to operate efficiently. When the craft approaches its upper heat limit, mechanical louvers placed around the body of the spacecraft allow excess heat to be radiated. When it approaches the lower limit, sensors placed within the craft alert the onboard automated heating system to keep the onboard electronics operating at approximately 100 to 120 watts. If the onboard electronics are not sufficient enough to supply heat to the spacecraft interior, small heaters placed around the interior of the spacecraft will activate using up to 15 watts of waste heat from the RTG. In order to retain heat inside the spacecraft during the latter half of our mission, a multi-layer insulation blanket will surround the craft. This blanket is comprised of Dacron, Mylar, and Kapton and will both insulate and protect the craft from small debris. In order to prevent the external fuel tank from freezing, it will be placed around the RTG like a sleeve. An aluminum heatsink weighing approximately 50 kilograms will be added to distribute the radiated heat around the tank to prevent boiling off of fuel from the concentrated heat exposure of the RTG.
Based on scientific discoveries of New Horizons, 4 instruments were selected for Lowell's orbiter. 4 scientific areas were selected for investigation: Pluto's subsurface structure and composition, atmospheric sampling, mapping and imaging, and monitoring atmospheric composition. The instruments have all been assigned TRL ratings and corresponding mass and power margins. All the estimated operational altitudes are below the maximum altitude during the orbit, and so there will be times during each orbit that each instrument can collect data. These instruments will be mounted around the gray belt shown on the model. The spacecraft will rotate until a given instrument is in the proper position with respect to Pluto to begin collecting data. RIME, or Radar for Icy Moon Exploration, is being developed by the European Space Agency's JUICE mission, and this will investigate the subsurface composition of mainly Pluto, but possibly Charon as well, since there is evidence that there is a subsurface ocean. RIME is based on Mars Express and Mars Reconnaissance Orbiter mission radar instruments. RIME has recently been field tested. Because of this heritage in testing, RIME has been assigned a TRL of 8. MassSpecs, or Mass Spectrometer for Planetary Exploration, will allow Lowell's orbiter to directly sample the atmosphere at low enough altitudes. By 2016, MassSpecs has been assigned a Level 6 TRL. Due to the uniqueness of each interplanetary mission, a specific camera has not been selected. However, a camera named PCIM, or Pluto Comprehensive Imaging or Mapping, will be a customized minimal mass and power camera. Parameters for PCIM have been estimated based on cameras on board past, present, and future missions, such as the Europa imaging system for NASA's Europa Clipper. Since Lowell's orbiter will be within the Pluto sharing system for some time, there is the opportunity to study how the atmosphere changes as Pluto progresses around the Sun. The ultraviolet spectrometer aboard New Horizons, ALICE, will be used to study the composition and structure of the atmosphere. Other spectrometers have been developed. These are Rosetta ALICE, LRO LAMP, Juno UVS, JUICE UVS. However, ALICE remains the most suitable for the Pluto sharing system.
Lowell's orbiter adapts the trajectory design used in the New Horizons mission and involves 10 subsystems to achieve mission requirements for an orbital exploration of the Pluto sharing system. Targeting a flyby at Jupiter, the spacecraft will launch on February 5, 2030, and reach the orbit around Pluto sharing system on December 2, 2051, then proceed with scientific measurements for 3 years and 2 months, which adds up to 25 years of maximum mission length given by the RFP.
The new objectives make the mission distinct from New Horizons with various refinements in the spacecraft components. Lowe's orbiter will utilize previous knowledge and experience from New Horizons with several improvements in the subsystems to meet the dwarf planet again before it travels even farther from the solar system along its orbit.